Hello, everyone. All right, so for science, what we're going to do is we're going to move on to looking at mass, weight, and volume. So we're talking about density primarily in this lesson. So let's get going here. I think I've solved the problem as far as not being able to see the Google Doc. I now have it where the slideshow is here on the same page as the notes. So I think we'll make this work. So open up your document. You're working from the same document that you've already been working through. So that means that with this was the previous lesson, so you should have that already filled in. And now we're moving on to here. So we're looking at mass, first of all. So with mass, now first of all, there is a cool little video that you can watch here. And this one is talking about the 1 kilogram ball that they created as a standard unit of measurement. So that's an interesting video there, just talking about how they came up with 1 kilogram and how they try to be able to compare that against others so that they keep it as a consistent, a constant standard of measurement, and that it doesn't fluctuate. It's pretty neat. So there's this video here, and what you get from it is that they are trying to use silicon 28 atoms as the standard for the kilogram compared to a physical weight. So you'll find out more about that in this video. And then let's go on, moving on here. So definition of mass. So the mass of an object or substance tells us how much matter it consists of. The greater the mass of an object, the more matter it contains. So looking here, we now know that the mass of an object tells us how much matter it consists of. And then obviously if you have a greater mass, that means it has more matter in it. And mass is measured, I'm not sure if you noticed it on here, but mass is measured in kilograms. So that's why they had that video that was talking about the 1 kilogram weight that they created. So measured in kilograms. You'll also see that as kg. That's that's an abbreviation for kilograms. So when we measure the mass of small objects or small amounts of matter, we often measure in grams or even milligrams. So it just depends on how big the object is. That's what they'll determine for being able to measure it. And then 1 kilogram, that's the same as 1,000 grams. 1 gram is the same as 1,000 milligrams. So, question, how many milligrams are in 1 kilogram? What can you decide there? I want you to see if you can figure that out. I'll give you a moment. I'm going to come back to that question. I know there'll be some of you who are motivated to find that answer. So if you can figure it out, how many milligrams are in 1 kilogram? If you know that there are 1,000 milligrams in 1 gram, and there's 1,000 grams in a kilogram. So going back here, the answer's right here. I forgot about that. All right, so we have 1 million milligrams are in 1 kilogram. I'll just go ahead and put it over here. You don't have to write this down, but let's do this. 1 million milligrams. That's how many are in 1 kilogram. And what's interesting here is if one gold bar has twice the mass of another gold bar, then it contains twice as many gold atoms. The mass of an object stays the same no matter where it is. Unless a piece of it is cut off, the same gold bar will have the same number of gold atoms, whether it is in Gotang, I don't know if I pronounced that. I'm going to leave those first 2 words for you to read, London or the moon. That means the mass will always remain constant. So I don't know if you've ever been to a science museum or anything like that, where they have all these different exhibits set up, where what they do is they tell you roughly how much you would weigh on different planets in our solar system. It's pretty cool. I know that they were saying that for the moon, you would weigh way less. I think it's about 1/6 of your current weight. That's how much you would weigh if you were on the moon. Whereas I think it was Jupiter, if I'm not mistaken, you would weigh the most there. And even though you don't change, as far as you still stay the same mass, your weight changes. And so here, often mistaken for mass, weight is actually the measurement of the pull of gravity on an object. So with Earth, we have a set gravitational pull, and so that's how we determine our weight based on that. Whereas if you're on the moon, your mass remains the same. You haven't, lost chunks of your body or anything like that. So yet you would weigh less on the moon, and that's simply because the gravitational pull on the moon is less than you would have here on Earth. And like I said, I think it's Jupiter that has, I think it's the planet that has the highest, or shall I say, the strongest gravitational pull. So that means you would weigh the most if you were on that planet. So I guess if you want to say you lost weight, just, go to the moon, and then there you go. You would have lost a big chunk really quickly. Oh, here we go. So 9.82, and this is the 1.62. So keep in mind that on the moon, it's 1/6 of the Earth. And a brick with a weight of 8 kilograms when measured at sea level on Earth will have a weight of 1.32 kilograms on the surface of the moon, simply because we have a different gravitational pull. So the force of gravity is much lighter on the moon compared to here. All right, I think you guys got that. So volume, we're just having it where we're going through here. There's not as many notes for you to fill in on your Google Doc today. It's more a matter of watching that video on the first slide, and then also having it where you just follow along in the slideshow presentation, and then we'll fill in some of the blanks as we go along. So taking a look here, volume, that's how much space matter takes up. So that's going to be measured typically in liters. It's calculated by multiplying the length, width, and height of an object. And so what happens is a liter is a space inside a cube that is 10 centimeters wide, 10 centimeters long, and 10 centimeters deep, because if you multiply them by each other, that equals 1,000 centimeters cubed, and that is the same as 1,000 milliliters, or 1 liter. So this cube would have a volume of 1 liter. Then density, so that's how tightly packed a material is. So I'm not sure if you've ever baked a cake before, but think of it this way. I am thinking of 2 different types of cakes. You might have it where you have an angel food cake, and that one, even though it's like quite big in size, it's very light and fluffy on the inside, in the sense of like it feels like you sometimes are almost like biting into air. Like it's very light. It's a nice light dessert. Whereas with something like a pound cake or something to that effect, that is going to be much more dense. It's a heavier cake. It's even heavier in weight. And it could even be a smaller shape than the angel food cake, but it's way denser. It's much more tightly packed in there. So that's what you can think about when we're looking at density. And it's a measure of how much mass of material fits into a given volume. And what happens is the mathematical equation to find out that ratio is density equals mass divided by volume. And so you've been doing algebraic formulas, equations in math. And so it's the same idea. So D equals M divided by V. And you end up having it where a common unit for density is either going to be grams per centimeter cubed or grams per milliliter. If we had 2 materials with the same volume, the material with a higher mass will be more dense. It will have a higher density. So just keeping in mind, we're looking at more like the lightness or heaviness of an object of the same size. Oops. So going back to that cake example, then look at this. This definitely looks like a nice, dense cake. It's very tightly packed, whereas if you were to cut open, let's say, an angel food cake, you would see a lot more space between the pastry in there. Okay, so now we're going to look at density here. And we have 3 identical containers. And so obviously you can see here that container A, that contains solid material, because look at how tightly packed that is, and it's all uniform. So it's uniform in its proximity to each other, and it's also very tightly packed. Whereas with container B, we see that it's still fairly tightly packed for sure, but it's a little bit more jumbled. It's a little bit more free-flowing rather than being uniform in its order. And then here we obviously have a gas that has very few particles, and there's a lot more space in between them. So they're just free floating in there. They don't really have any kind of order to those particles whatsoever. All right, now we're going to go on to the next one here. So just think about this here. Which container, A, B, or C, contains the greatest number of particles? And then which container contains the smallest number of particles? So you should be looking here where obviously it's pretty obvious that container A, the solid, obviously has a greater number of particles, so it has a greater density, whereas the gas contains way fewer particles, and so it has a lighter density. And then moving on to the next one, looking at mass here. Now here we also still see though that, and looking at these three containers, we see that even though they're the exact same size, and exact same shape, they have where the solid still has a greater mass compared to, let's say, the gas. The gas would have the smallest mass, fewer particles in there. So the particles play a big role in density and mass. And here we have which state has the highest density. Again, you have the same answer. We see here that the solid is going to have the greatest density. It has way more way more molecules that are tightly packed in there. So it's going to be heavier compared to, let's say, gas. I'm sure you've had it before where if you've, let's say, picked up let's say a Tupperware container, they're the exact same size, and one of them has, oh, you know I love steak. So let's say one of them has a nice juicy steak in it, and the other one just has air. Well, obviously the one that has the steak in it is going to be heavier compared to the one that has simply air. All right, so we have lower density there. And then why solids are more dense. So the high density of a solid material explains why it cannot be compressed. So remember how we talked about that last lesson, how solids are the hardest to be able to compress compared to liquids and gases. And obviously liquids are still kind of difficult to compress, but a little bit easier than a solid. And then gas would be the easiest simply because the molecular bonds between the particles are easily broken. So liquids still are very dense. Remember what I said though, that what happens is that it is actually roughly the same as the solid state of the same substance. And that's because the particles are still very close together, even though they're not locked into fixed positions. So some liquids can be compressed into the smaller volumes, like I mentioned, but a lot of them actually can't because they're still too dense to be able to easily do that. But there is one exception, and again, we looked at this briefly last lesson as well, that ice is our exception because the ice will float to the top of the water in your glass. And the reason for that, if you remember from last time, is if you take a look here, look at the water molecules in the liquid state, they're still quite tightly packed together. They are, they're definitely harder to break those bonds, whereas here in a solid state for water we see that they have open spaces in between the molecular bonds, which means that they're much more easily broken, and they are going to be able to rise to the surface if they are put into water or another liquid because they're going to have a less density compared to them. So that would explain why icebergs, they're huge, they're heavy, yet they are able to float in the sea. And with gases, we know that gases, they are not dense at all. They're easily compressed because they have large spaces between the gas particles. And think about, like, let's say if you're going scuba diving. So remember how we looked at that picture last time? If you're going scuba diving, you're going to have an oxygen tank. And you have all this compressed air in there, so that way you can be able to last underneath the water for a significant length of time. And so it's actually quite handy that we can have compressed air, which is awesome. I think that's almost towards the end here. So here's the deal. I have this diagram here that shows density, mass, and volume and the relation there. So if you have, let's say, density, so going to this one here, if you're trying to find density, you know that, okay, mass needs to be divided by volume to be able to find out how much the density is. So it says here, a student measures the mass of an 8 centimeter cubed block of brown sugar to be 32 grams. What is the density of the brown sugar? Now you might be tempted to say that the 8 centimeters is the mass. It's not, because it just said here, it measured the mass of a certain block, and that mass was found to be 32 grams. So if you were to do the math, and you would have it then where, okay, so the mass is 32, and the volume is 8. So that means it's going to be 32 divided by 8, just like they have here, which then gives you 4 grams per centimeter cubed, and that gives you the density there. So looking back at our document, we have explored with density, we explored how ice is so much lighter compared to water or liquids in general typically, and that's because of the unique structure of the molecular bonds between the particles within solid or within ice. Now, this page here, so again, obviously with this lesson here, it actually is an easier lesson simply because you don't have as many notes to fill in. You are welcome to give this a try using that formula of density equals mass divided by volume. You're welcome to see if you can answer these questions and see how it goes. But realistically, you only have to go up to page 13 here. And what I'll do is I will have a Google form with some questions from this lesson, and just fill that in for your homework check and you'll be done. So this is a bit of an easier one today. I hope you are doing well, and I will see you for next lesson.